This is Mr. Forrest, and I want to go over a couple examples of bar charts again, both for people who have been absent, as well as leading into part 2 of the bar charts, which is more mathematical and quantitative. So if you remember the formulas we gave you in class, they are kinetic energy is equal to 1/2 times mass times velocity, or speed, squared. Gravitational potential energy is equal to mass times gravitational field strength, which is about 10 newtons per kilogram, times the height, that something's elevated above a zero position, or where you choose to have a zero position. And elastic potential energy is equal to 1/2 K, which is a spring constant, multiplied by the amount of stretch or compression squared. And we symbolize that with the letter X. The other thing we're going to find out is that work is equal to force times distance, and sometimes there'll be a cos theta in there, which we'll talk about, but for the most part it's going to be force times distance, or displacement, which is F times X. So those are the equations. Anyhow, these three examples I wanted to be done in class, but like I say, I wasn't expecting to be at this exact point when I was asked to go to this meeting. So this is a qualitative one. This is similar to ones we've done. So the idea is a bungee jumper falls off the platform and reaches the limit of stretch of the cord. I chose no friction. So this is the zero height. I'm choosing the earth, the person, and the bungee to be in the system, so that's pretty much everything. The initial condition is they're up here, final condition is they're down here, and they're not moving at the end. So initially I'm going to say they have all gravitational potential energy. I chose 4 bars, but that's an arbitrary decision. At the end, they're hanging down here. They're not moving. I'm glad they tied it to their foot at least. And it looks like they're a little above zero. So I still had 1 bar of gravitational potential energy, and then I said that the bungee was stretched, and so there were 3 bars of elastic potential energy. So that should be pretty straightforward. Example 2 is a challenging example, and it's numerical, so I want to make sure we talk about that. A 2,000 kilogram elevator is at a height of 40 meters, so it's initially here. It's moving downward initially at 4 meters per second, and is brought to rest by a braking system. So if there was no braking, this would go faster and faster and crash into the ground. So you want to find the final amount of energy transferred to the braking system. And the question is there friction? Well, there's brakes, so yeah, there is. But this is a little unclear. This dashed line here is the system boundary. And by the way, these examples are on the back of the work energy bar chart handout I gave you. So this should include the earth. It does include the elevator. It includes this rope. It does not include the braking system, which is up here. So at any rate, this initially it was elevated and it was moving, so I gave it some kinetic energy, some gravitational potential energy. I don't care about the exact amounts you have here, but it has some of each. At the end, it's not moving, so it doesn't have any kinetic energy. It's not elevated, so it has no gravitational potential energy. I did not think of this cord as being elastic or stretchy. You kind of wouldn't want that on an elevator, because that would be a weird ride on an elevator bouncing around. So I put this as 0, and I had 0 internal or thermal energy. And the reason I had that is the braking system is outside the system boundary. So if I start with what looks like 4.5 bars, and I end with 0 bars, I have an arrow pointing out from this energy flow diagram, and that says it's going to the brakes. So now if I want to think about the mathematical answer, I can say I start off with kinetic energy and gravitational potential energy, and at the end I have work. So you could either put EK plus EG is equal to work, or EK plus EG minus the work done by the braking system is equal to 0. I think I like the first way I said, where EK is equal plus EG is equal to work. So if EK is 1/2 m times v squared, and EG is mgh, I should have put those down first. Should have put the general formulas down first, and I didn't. So sorry about that. Anyhow, 1/2, 2,000 kilograms, 4 meters per second, and you've got to square the 4, so 4 squared is 16. 16 times 2,000 is 32,000, times a half, 16,000 joules of kinetic energy. The gravitational potential energy, 2,000 kilograms, times 10 newtons per kilogram. You could also use 9.8, but I like using 10 because it makes my life easier, times 40 meters of height, is 800,000 joules of potential energy. So that says that I have 816,000 joules of mechanical energy initially, and at the end I have 0. So therefore, 816,000 joules has to be transferred to the braking system. Those brakes probably get pretty hot. So the idea here is to think about this more mathematically. Obviously, these are not to scale. I didn't anticipate this, but the gravitational potential energy is much, 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 much more than the kinetic energy. So that's interesting. I've got a third example here in the back. So this says a block is placed on a spring, compressing at 0.30 meters. At what height does the block reach when launched by the spring? Assume no friction. My system is going to be earth, spring, and block. I've got a spring constant of 100 newtons per meter. The delta x, or the compression, is 0.30 meters. The mass is 500 grams. And at the very tippy top, the velocity is 0. So I've got an E elastic at the beginning is equal to E gravitational at the end. I have 1/2 kx squared equals mgh. So 0.3 squared is 0.09, times 100 is 9, times a half is 4.5, so 4.5 joules. 0.5 kilograms times 10 newtons per kilogram times h is 5h. So this says it would go up 0.9 meters. So what I didn't do, and I need to do here, is I need to show this in terms of my bar charts. I didn't do that very well. So I'm going to start off with elastic. This is weird. Put this right here. Let's make it a nice purple color so that way I can pretend that I did it right to begin with. Good. Oop, and the border color, do black for that. And then I'm going to copy and paste. I'm going to move that over here, and that is gravitational. I don't know why this is being weird when I try to move it. Okay, so that looks pretty good. Ha! It's like I did it right the whole time. Okay, so those are some examples, and hopefully those make sense.